Okay. We are live now. Can anyone in the chat confirm that you can hear us? So there is a small delay with the StreamYard. So there is a like 10 seconds delay and then you
Okay.
type it out and YouTube
Yeah,
shows you.
it should be fine. So I guess when people ask questions, it's 10 seconds in the past.
Yeah, kind of.
Okay.
Okay, so we are. Okay, so I think the comment section is off. Ayush, can you see that? Okay, so
It's working now. It's working now. Live chat is
loud.
working.
So we have it here. We have us. We have Lerrel Pinto. Uh, let's start with the introduction of the people here. So Ayush Sharma, he's the MLRW convener of this year's. Myself, I'm Varun. I'm secretary of ITs.ai. And we have with us Lerrel Pinto, who is an assistant professor at New York University Courant. He generally works with robotics and machine learning in general. So he has done a lot of cool stuff. You can check out his website. It'll be really good. So let us start with the talk today. That is, so it's over to you.
All right. Yeah. Thanks again for the introduction. So first of all, I should say that this is a great initiative, right? So when I was at IIT Guwahati, we didn't have initiatives of this sort. So I think this is it's really great that that you are all organizing this. So with that said, we can get started uh, with this talk. So feel free to interrupt and ask questions. So if things are not clear, you should just post on YouTube for um, or the moderators can also ask questions. In general, I'll be speaking about works that are quite new. So most of the works I'll be talking about were either on archive or published in just the last 2 or 3 months. So they may still be a little raw in some sense. So it'll be great to hear questions on them. All right. So to begin, I think the central question that we are trying to address in our group is how do we make robots that can generalize into the real world, right? So what does this mean? So we know that humans are able to operate in environments that are quite complex, right? So this is a video from Marie Kondo's show on Netflix where she goes into people's houses and help them clean up their place, right, or organize their life. Um, so what it I think shows you is the sort of rich visual diversity and unstructuredness of the real world, right? The world is not like a lab or an industry where everything is like well organized and everything is kept in place. You know, everything is in the right place. Okay, so clearly we don't have robots that can do the things that humans are able to do in these sort of environments, right? So the question we're asking is how do we make robots also interact in these sort of interesting and complicated environments? Okay, so before we get there, clearly we don't have those robots right now. So let's try to see what are the reasons for it. Why don't we have robots that can interact in these sort of environments? So I think there are three main reasons for this. The first one is image-based observations. So what does this mean? So let's say you're a self-driving car, right? So you're on the street, you have a camera on your self-driving car, and from this camera, what you're able to see is this sort of visual observation, right? An observation of cars, people, the road, etc. Now, this raw visual observation is quite high dimensional, right? So if it's a 2 megapixel image, it's going to be 2 million in dimensions, right? So now reasoning, if you're asking a robot to reason from this high dimensional observation, it's going to be quite hard. It's going to be quite challenging to do so. But we also know that when you look at this image, the actual information in it is actually not 2 million in dimensionality. We know that the things that actually matter in this image, things like the location of the car, location of the person, where the road is, etc., is actually quite low dimensional, right? It may just be a few hundred dimensions. So, of course, one obvious strategy here is if you have to reason with these high dimensional observations, what you can do is first extract this low dimensional state, right? And then do interesting things or do intelligent things with this state, with this low dimensional state. And this is a common strategy employed in robotics. So, for instance, if you look at self-driving vehicles, they often have these really complicated sensors like lidars and ultrasound, collision sensors, etc. And even for manipulation problems, if you have to try to figure out where objects are in the scene, you often need this sort of complicated rig around it to get accurate state information. So hopefully this sort of conveys the idea that estimating this low dimensional state is actually quite hard in the real world, right? And hence we want to figure out algorithms that do not necessarily need to estimate the state in the real world. Now, I think there's another reason to not estimate state in the real world. For a lot of different objects, the state is like ill-defined or even too high dimensional. So, for example, if I show you a piece of cloth, right? I show you a piece of cloth that is being ringed around, or if I show you a piece of rope that is being knotted, what is the state of that piece of cloth? How do you describe what the state is of this rope? And then even if you look at other examples, like if I show you an image of a tree and I ask you, what is the state of this tree? Are you going to model every single leaf on this tree? That's probably not going to work so well. And again, if you're trying to clean up something, are you going to model every single speck of dust? Because if you're doing that, it's going to be a very, very high dimensional state to deal with. Okay, so the first issue we have in robot learning is how do we create algorithms that can deal with this high dimensional visual observations? The second issue is reasoning over long horizons. So again, to explain about this, let's take a look at a scene again. So you have a self-driving car. It's seeing this observation from its cameras. And now let's ask a question. What is in this image? To answer this question, it's actually quite easy. You just go to clarifai.com, upload this image, and you'll get your results. You'll get that there's an adult, there's a person, car, street, road. Right? This is we already have we already have good supervised learning algorithms to solve this problem. But what is sort of less clear is if I ask a slightly different question. If I ask, where should I go? Answering this question becomes a lot harder. Right? And the reason it becomes hard is because answering this question requires you to solve a sequential decision making problem. So, what this means is that at every observation, if you take some action, right? So, let's say you're seeing an observation x0 and you take an action y0, let's say in this case it's going left, you would crash into oncoming traffic and then you would see a new observation of your crashed car x1, and then you have to apply actions after that. So what's happening is that whenever you output something from your model, that output is affecting what you see next. And so now when you have to make a decision, you not only have to make a decision about what's happening right now, but you also have to make a decision about what's going to be the best thing to do over a long horizon of time, over a long amount of time. Now, one way to sort of address this problem is to recast this problem into a one-step sequence. So instead of looking at a n-step sequence, you look at a one-step sequence. You can also look at this as a contextual bandit problem. And over here, if you look at it in this sort of a problem, we have been able to use this formulation to do things like figuring out how to grasp objects, figuring out how to fly drones without crashing everywhere, and even bring some of these robots into real world homes. Now, of course, a challenge over here is that it's difficult to recast a general robotics problem as a one-step sequence. And so we really want to create algorithms that can sort of deal with a general problem and not need to stay with only a one-step sequence. Okay, so this is the second challenge we have. How do we reason over long horizons? The third challenge we have is dealing with the changing world. Okay, so let's say you go onto Instagram and you're like trying to figure out what cats look like. So I go onto Instagram, I search for cats, and I see very well aligned, very well photographed images of cats, right? And I try to build a model of, okay, this is what cats look like. Then when I go to the real world and I actually look at cats in the real world, the cats don't look anything like what I've seen on Instagram. Right? And so what we have over here is when we have sort of learned about what a cat looks like versus what we are actually observing in the real world, there's a big mismatch in this. Now, how do we address this mismatch? This is a very important question. So on a more serious note, let's say you have, again, a self-driving car, and I train this self-driving car on the streets of New York. So you can see some images from New York over here. Um, and if I train a model which either is trying to drive or trying to recognize objects or recognize vehicles in New York, if I now try to deploy this model in New York, it will work quite well, right? Because the test set, it's sort of it has a high intersection with the train set. But what is a lot harder for machine learning models is if I show you examples or try to deploy the model in settings which are not in New York, right? So I think the one on the bottom left is from Sri Lanka. The one in the middle, it's in the nighttime instead of the daytime. And the one on right is like on a snowy condition instead of like a nice sunny day. So in all of these cases, you have a deployment which is not the same as your training, right? And so model would not work as well there. Okay, so this is the third challenge we have. How do you create algorithms or models that can deal with a changing world? All right, so just to summarize the three challenges, we first have uh, creating algorithms that can sort of use high dimensional sensory observations. We then need to figure out how to do credit assignment for long horizon sequential decision making problems. And then third, we need to figure out how we create algorithms that can adapt to a changing world. Now, to solve these three problems, in this talk, I'll present one algorithm each. So for the sensory observations, I'll present an algorithm for representation learning. For the credit assignment problem, I'll present an algorithm in reinforcement learning. And third, for a changing world, I'll present an algorithm for adaptation. Okay, so before I go ahead, are there any questions?
Right now, there doesn't seem to be any.
Okay, so let's go ahead then. So let's get started with the representation learning problem. So the first question is, what does it mean by representation learning, right? It seems, um, at least in the void, it seems like it doesn't have much meaning. So I want to first give like a quick sort of primer on what it means and the way in which we use it. Of course, there are multiple ways to view a representation, but we view it in a very specific way.
Hello.
So let's say, oh,
Hi, sorry to disturb you, but there's a
yes,
question from Aditya. Are you looking at meta learning too?
no. So we do have algorithms that are sort of like we can compare with meta learning approaches, but we don't focus specifically on meta learning approaches. Okay. All right. So let's get started on what exactly a representation is. So if you have a high dimensional observation, let's call it OT. It's on the left, right? So this is a high dimensional image that we're seeing. Now, what we're going to do is we're going to have an encoder, which is oftentimes a neural network, a CNN, right? And it's going to take as input this image and output an encoding, which is going to be low dimensional, let's say a few hundred dimension. Now, this encoding which it outputs is what we're going to call a representation. And the process of learning this encoder is what we're going to call representation learning. So the sort of hope is that if you are able to learn a good representation, you have this low dimensional encoding or feature, which you can then use for a downstream task. So for example, if I have a good feature or a representation, I can use that feature to do optimization for a robot. Either I can use like imitation learning, I can do model free RL, I can do planning, I can do lots of things with this feature once I have a good feature. Okay, so let's see how we can use this feature in one of these examples. So first, let's look at imitation learning. So what exactly is imitation learning? So in imitation learning, what happens is you have a human, over here you can see these humans. What they're doing is they're holding the hand of the robot and moving the hand of the robot in order to show the robot how to solve a specific task, either how to pick up objects, how to draw the name of uh, like a name on a piece of paper, right? And so by moving the robot and showing the robot how to move it, the humans are giving a demonstration to the robot of how to solve the task. And then imitation learning is basically a robot learning algorithm where, given these demonstrations, the robot needs to figure out how to imitate those. They need to figure out how to imitate what the human was trying to do with the robot. Um, Now, there are multiple ways of giving a demonstration. The way I've showed, so the videos I've shown over here, these are called kinesthetic demonstrations, right? Because the humans are actually holding it and showing it by hand holding what it needs to do. A challenge with these sort of demonstrations is that they are actually quite difficult to do because you need to hold the hand of the robot, right? So you need to figure out how the robot's hand moves, right? It's often slow because you need to first learn about how to use the robot, and then it's limited to lab settings. Right? So if I want to show a demonstration, I cannot go out there in the real world, right? Because if I have to go in the real world, I have to first move these big, expensive robots into the real world. Okay, so going through a kinesthetic demonstration is probably not going to scale when we go into the real world. So to fix this issue, what we did is we created a new way of obtaining a demonstration. So we use assistive tools, and the whole framework is called Demo 80. So the way it works is we use a reacher grabber tool like the one you can see over here. So this is like a common reacher grabber tool which has the two fingertips, which is also called the reacher grabber. And what we do is we modify this and attach a camera on top. This is just a GoPro camera attached through a 3D printed mount. So what you have over here is this tool which you can move around, you can interact with the world. And as you interact with the world, you're getting these like rich visual observations from the GoPro camera. On the robot side, we have exactly the same setup almost. So again, we have attached the stick on the robot, right? So it has the same reacher grabber, right? And it also has the same camera attached to it. So this means that when I show you a demonstration from the viewpoint of the camera, it doesn't know if it's coming from a human or if it's coming from a robot, right? Because the camera is attached on the hand, which means that once I show a demonstration on the tool, those demonstrations are also valid for the robot. Right? So it's like a interesting way of obtaining a demonstration without actually even interacting with the robot. You just move the stick around and the robot can now see what it needs to do. Okay, so this tool is quite versatile. So here are a few examples of using the tool. You can use it to manipulate objects, clean whiteboards, open doors, drawers, throw away trash, fetch your keys, right? So there's lots of things that you can actually do with this tool. But perhaps more importantly, what you can do with this tool is you can go out there in the real world, right? So I can take this tool, I can go to your home, I can go to my home, I can go outside on the streets and use this tool to get interesting information and data in the real world. Okay. So if you're interested more about this tool, have a look at the reference at the bottom of the paper. So for example, if you're interested in how we obtain actions from this tool, how we figure out how the camera has moved, all of that information is in the paper below. So now let's see how you can actually use this tool for a specific task, right? So let's look at the task of door opening. So in this task, what we want is we want a robot to figure out how to open a door like this one over here. And what we're going to do is we're going to show a demonstration by using this tool to open the door. All right. And after it does this, we want our robot, which is this hello robot on the right, to sort of solve this task. And so when it does solve the task, it will look something like this, where it's going to the door, it figures out where to grasp, and then it opens the door. Now note that when it's doing this, the only information it has about the world, about where the door is through the camera on the hand of the robot. There's no other information that it has about the world. Okay, so how do we go about doing this? So uh, before we go with our method, let me just give a quick introduction into a prior method, which is called behavior cloning. So the way behavior cloning works is that you learn a neural network where the input is observations. So the observation, it can be like image that you see while you were moving the tool around, right? So it's the observations uh, for the robot, and then this model has to output actions. So in our case, the action is the end effector velocities. So it's like the hand of the robot. What's the velocity in which it's moving? To train this model, we just use supervised training, right? So this model is trained end to end, right? So this is how normal behavior cloning is done, right? And now since it's trained end to end, one can sort of intuit that you would actually need a lot of data to train this model, right? Because this model is taking in raw observations, it's going through multiple layers of a CNN and then outputting an action. And so in order to learn this mapping from image observations to actions, you would need a lot of data to train this whole neural network. So of course, in the case of imitation, what this would mean is you have to give lots and lots of these demonstrations, right? Which is not what we want to do. We want to train our robots with just like maybe like 20 demonstrations, right? So yeah, so we need to figure out a way in which we do not need these large data sets. Okay, so what we do instead is first we use our model only to learn a representation. Right? So we're going to take observations and we're going to output a representation, right? And as you can see in this model over here on the right, there is no information of action right now. So when we learn the representation, the information of action is not used at all. Once we do have a representation, the way to figure out actions is that, okay, so let me just skip this part. So the way to figure out actions is to just do nearest neighbor matching. Right? So you look at your demonstrations, you look at what are the closest examples in your demonstrations, just do nearest neighbor matching on that. And from nearest neighbors, you can figure out what the action is. So let me explain this in a little bit more depth on how it is actually trained and how the execution actually works. So let's put this model in the center. So in training time, what we do is we have to figure out a way in which to learn a representation without using information of action. So what we end up doing is doing self-supervision. So in self-supervision, what happens is you take these observations, you do augmentations of the same observation, and then you try to train this encoder that outputs a representation such that the two representations, so the two augmentations, are the same. So you're going to do augmentations, but then after encoding, those two augmentations should lead to the same representation. Now, there are multiple ways to train these self-supervised algorithms. The one we do is called, or the one we focus mostly on is called PYOL, but there are lots of other algorithms which are also compatible with this framework. Okay, so after we have our encoder, what we do is now, as our robot is in the world, it sees an observation. We first extract a representation through the encoder, and then for execution time, we use nearest neighbors. So the way this works is when I see a specific observation OT, I extract the representation, and then from my demonstration data, I match my representation with what I've seen in the demonstrations, right? So let's say I have like a bunch of nearest neighbor matches, as you can see where my cursor is, right? I know what the actions are in the demonstrations, right? So I know what for each of the matches, I know what the action is, and then I just weigh those actions. Like I just do a weighted sum of the actions, where the weight is inversely proportional to the distance between the representations. So if I have a demonstration where the image is very close to what I'm seeing right now, I'm going to apply a very similar action. This method is called locally weighted regression. If you're interested in it, please feel free to search more about it. All right, so this is how training works. Know that in training time, there's no information of action, so we have to do self-supervision. In execution time, there is no learning happening here. It is just nearest neighbor matching, right? We're just using the learned encodings and then doing nearest neighbor matching in execution time. So this algorithm is called visual imitation through nearest neighbors, or VIN for short. Um, Over here, I want to just give you some videos of what the demonstrations look like. On the left-hand side, you can see from a third-person view what it looks like to sort of open this door. On the right-hand side, we show what the first-person view is, or from the view of the stick, what the video looks like. So note that what you're seeing on the right side is what our neural network models are also seeing. It is what our robot is also seeing. So we have to operate with these sort of visual observations. Okay, so now let's see how this model works in action, right? So I have this
Hello.
robot. Yes.
There's one question from Ashik. Uh,
Yeah.
can the robot not learn by using a reward algorithm using reinforcement learning?
Yeah, so you can use reinforcement learning, but you have to specify the reward, right? So how do you specify the rewards over here? So that's the first question. The next question is, with reinforcement learning, you need lots of samples to learn from those rewards. In this case, we only have like 20 odd demonstrations, and immediately after that, it's able to figure out how to open the door. There's no online learning happening here. You just show it a few demonstrations, and immediately after you train on those demonstrations, it's able to solve the task and open the door. If you're interested in reinforcement learning, in a few slides, I'll be talking a little bit about reinforcement learning. All right.
There's a one more question. You
Mhm.
explained all the imitations and approaches. How much time does it take, or how many iterations does the bot need to understand to learn these tasks?
So for this task, what happens is there's a human with the stick, right? So the human with the stick has to give maybe 20 demonstrations. So in this specific door opening case, with 20 demonstrations, it can learn. So you show 20 demonstrations, right? You have all the data. You send the data to like a desktop computer that's doing training. It's trained a model. Once it trains the model, immediately you can use this model and run the model on the robot, and the robot will be able to open the door. So on the robot, there is no online learning on the robot. The robot is just going to output actions, and it's going to open the door. I don't know if that clarifies it. Um,
Yes, yes.
okay. Um, okay, so let's see this model in action. So let's say our robot is at this state. It's like close to opening the door. The observation which it sees is something like this, which is inset on top over here. Now, from this observation, I'm going to first find nearest neighbor matches. So here are my 3 nearest neighbor matches, right? Now I know what the actions were, which is denoted by these red arrows, right? So these are the actions which I've seen in the demonstrations. I then do locally weighted regression. So that's just like a average, like it's like a weighted averaging process of these actions to figure out what the action I need to take on the robot. Then I apply this action. My robot moves in front. It sees a new observation, right? And then it just repeats this process over and over again until it's figured out how to open the door. Right? So if I just keep playing this now, it'll just show how the robot moves and what it sees and the output actions in the inset image. All right. So let me actually skip this one. Okay, so what we're able to see is that if you use the specific algorithm called Win, you get a very high success rate. You get around 80%. And this is not just on this one cabinet door, but we experiment on multiple of such doors in our NYU kitchen over here. We also experiment against lots of other like strong baselines. The one that the one baseline that works the best is if you do behavior cloning on self-supervised features or representations. That actually works quite well, but it's of course not as good as our algorithm. You can also try just using ImageNet features, for instance, and do nearest neighbors on that. But again, that also it doesn't work as well because ImageNet features are not tuned for the specific environments that we are in. So you actually need to see the data of our environments in order to learn a feature that is good for those environments. Okay, so after this, we were like, okay, this we have a model which is able to figure out how to open a door. Let's actually try to see how to break this model. Right? So what we do is we now use this model over here, uh, but we now add like visual distractors. So we either add tape on the scene, right, or we add like some like sheets of paper to just obfuscate the visual features. And in most cases, it works quite well. The model is able to figure out still how to open the door. The place it fails is if you obfuscate almost all the visual features, right? If you like tape like all the information, then it starts to fail, right? Because it now has no visual feature to latch onto and to find good nearest neighbors. So again, we're able to see that our method is able to do better than the baselines, especially when you sort of try to mess with the environment and add these sort of obfuscations. All right, so all of the paper code and the data is on this link over here. If you're interested, feel free to learn more about it over here.
We have one more question from Abhilash.
Hmm.
How
Hmm.
does a bot know how much force needed to apply to hold an object? Let's say between the steel door handle and an egg. Is it possible to check if the model learned hardness of the object?
So over here, there's no model of force, right? The only action that this robot is applying is velocities and open close instructions on the gripper, right? So that's, I think, a very good question because it's sort of, I think it's like a limitation of our work at this point where we're not looking at forces, right? So we can only do tasks where it doesn't really matter how much force you're doing as long as you're acting slowly, right? So if you see how the robot moves, it moves quite slowly. All right. So now let's move on to the next part. So I've talked about using representation learning algorithms to deal with these sort of high dimensional visual observations. Now let's look at the reinforcement learning problem. Okay, so just as a quick primer on reinforcement learning. So what happens in RL is you have an agent, you have an environment. Agent applies actions in the environment. The environment, it returns observations and rewards to the agent. Now, the goal of the agent is to maximize rewards, right? This reward is some notion of success. So now for the agent to maximize these rewards, the way it can do it is by figuring out what the right actions to apply in the environment. This process of maximizing the rewards by figuring out actions is called reinforcement learning, right? At least it's reinforcement learning is one of the main algorithms to solve these type of problems. Now you can do reinforcement learning either in visual domain where you have raw image observations, or you can do it in state domain where you have these low dimensional sort of this low dimensional state of the world. Now, of course, it's easy to intuit that when you try to train these type of algorithms, it's going to be much easier to learn when you're with when you have low dimensional state than when you have high dimensional visual observations. Right? And this intuition is also, in some sense, supported by prior experiments. So this is prior work. It's from 2018. So on some standard tasks, so let's have a look at the plot on the left. So in blue line, it is what happens if you do state-based learning, state-based RL, right? So this is with low dimensional states. And in the green line, it shows what happens if you do with image-based RL, right? So clearly there is a big difference between training with state-based and training with image-based. In fact, training with image-based is oftentimes like an order of magnitude slower. So how do we go about solving this problem? One of the obvious answers is to do representation learning, right? So instead of just doing RL on this high dimensional observation, we're first going to encode it into a low dimensional feature or a representation. And then from that low dimensional representation, we're going to do RL on top of it. And if this feature was somehow equivalent to the true state, then we know that we would be able to move the plot from the slow learning curve of image-based RL to this sort of fast learning curve of state-based RL. So this sort of idea has inspired lots of prior work. There are a lot of interesting ideas over here that if you're interested, you can read more about it. What we did is we're trying to take inspiration from vision and NLP. And in vision and NLP, more recently, what you're seeing is that the key idea to make things work is to look at augmented data, right? So if you look at recent work in self-supervised learning, for instance, they all use these augmentations of data. Okay, so if so what's the most easiest way of using augmentations of data, right? Or data augmentations. So we released this work, which it's a very simple idea. So you just take a standard RL algorithm, right? And instead of feeding it the raw image observations, what you do is you augment the data, right? So you apply like some small visual augmentations. Either you do like cropping or you do like a random shift, like a small augmentation. You then extract the feature and then just use that feature for RL, right? So it's like a very small plug and play module. You just insert it into the RL algorithm. It just applies augmentations, extracts a feature, and then uses that feature for doing RL. And this sort of simple idea, it actually works quite well. And in a lot of studies, we are able to show that doing this simple augmentation can actually narrow the gap now between image-based RL and state-based RL. So in these plots over here, let's look at the top left. State-based RL is in the gray line, right? Using this augmented data, so there are two algorithms over here. Both of them use augmented data. One is in red and one is in blue. So both of them are able to get quite close to this gray line. But if you see these plots, you'll notice there are some cases in which state-based RL is still quite good, right? So for example, if you see this swing up sparse task on the top right, the state-based RL in gray is still learning much faster than this image-based RL. And even for other tasks, like you look at this finger turn hard task, again, state-based RL is doing a lot quicker. So we were trying to figure out why exactly this is happening. And in this process, we created a new algorithm, which is called OctoQ-V2. So this algorithm again it does the same thing where you take observations, you just apply augmentations, and after you do augmentations, you feed the feature of those augmented images into your RL algorithm. Right. So the specific RL algorithm we use is it's called DDPG. Yeah, so that's a specific one we use. But in terms of a technical insight, there are actually no new technical insights in this paper, right? So in this paper, what we show is that if you get the details right, right? So here's a big laundry list of all the details which we had to explore. But once you figure out these details, what you can get is really improved performance in visual RL. So here, just to show that, I'm showing a plot of average rewards across 12 tasks. So this is 12 tasks from a standard benchmark called uh, EM control. In the blue line at the bottom, you can see what happens if you just do normal image-based RL without any augmentations. In the green line and in the violet line, it shows what happens if you do image-based RL using prior state-of-the-art algorithms which do image augmentations, right? And in the red line, it shows what happens if you use our new algorithm, which is just getting all the details right. Okay, so this is averaged across 12 tasks. So what happens on the hardest task, right? So the hardest task is this task called humanoid walk, or it's at least one of the hardest tasks. And what we see over here is like most of the prior methods, they just flatline. They're just not able to learn anything for like 500 hours of training, right? But our method is able to sort of solve this task in around 86 hours. And you can see that this is quite a significant learning rate over here. So this algorithm, I think, is right now the state of the art on visual RL, at least on the DM control suite. You can use this method to train agents like this solely from visual observations, right? So these agents are figuring out how to walk, how to hop, just from the same visual observations that you are seeing. Right? It doesn't have information to its even to its own state as it's figuring out how to do all of this. The code for this is all online. We have also tried to make an effort to make this code really fast to run. So hopefully it should be accessible to everyone who has like a laptop or something to run these algorithms. All right. So I've talked about reinforcement learning. If there are any questions, I can take them now.
Yeah,
Hi, yeah.
there are a
Yeah.
couple of questions.
Yes.
First one is, can the learned weights or parameters from one bot be used for another bot, like transfer learning? That's common with
Yeah.
learning.
Yeah, this is a really, really great question, actually. It's a problem which is there in RL, I would say, where if you look at vision, NLP, and all those other fields, like the way those fields work is you very easily train a model in one domain and you can transfer it to another domain, right? But in RL, we haven't seen this to be the case yet. What we're able to do, so this is like even more recent work. So we have shown that for a specific agent, let's say I choose a walker agent over here, right? If I choose a specific agent, I can now share information for two tasks using the same agent. Right? So let's say there's one task of going and running in front. There's another task of running backwards. Another task of doing a backflip. Right? I can do some sort of sharing across those, but I cannot, at least until now, we're not able to do sharing between one morphology and a different morphology in a sort of scalable way.
Okay, thank you for that. There is another question. Is there some special technique or algorithm to train the encoder so that it learns the most uncorrelated features?
So here's the interesting thing. So let me actually go back a few slides. So this method in red, right? It's called curl. So curl uses an unsupervised sort of unsupervised feature learning or unsupervised representation learning algorithm to learn the features. So they do this thing called I think it's Moco. I think they do Moco on the features. So it's a contrastive learning based approach to learn a feature which has which is a good unsupervised feature. But we see that like those actually don't really matter as much as the augmentations you need for these tasks. Right? So maybe for harder tasks, maybe for more real world tasks, we may need to use like some sort of unsupervised feature learning. But at least for these tasks, which is from a standard benchmark, You do not need a you do not need that. Yeah.
Quick
I have one.
summarize.
Yeah, like there was this previous question about transfer learning. So I have a question. Like you told about that transfer learning is not possible in reinforcement learning. Like, is it possible in demo IT? Like here, like what we are doing is like just picking something or like opening something at different
Hmm.
locations. So like,
Hmm.
is transfer learning possible there?
Yeah, so over there, actually, when you learn a feature over there, so there we are doing unsupervised learning, right? So we're doing sort of self-supervised learning. So we first do self-supervised learning, and then we use those features and do nearest neighbors on top of those features, right? So in that case, we can definitely do transfer learning because we are sharing all that features, right? We're sharing all the encodings, right? In RL, I think so. So maybe I should clarify. I think it should be possible to do transfer learning. I think it's just harder to do it in RL than in the other fields. Like it's not as standard in RL as in the other fields. And then from that point, I want to say that in the demo AT work in Win, for instance, over there, I would view that more like it's approaching the problem like a computer vision sort of problem, right? We're saying that we have this large, or maybe not large, but we have some amount of visual data. We first learn self-supervised learning purely on the visual data, right? There's no information about action when we are first learning the feature. So because of that, this feature should now work across lots of other domains.
So yeah, so like in that, like we are doing these things physically, these experiments again and again physically. Like, is it
Mhm.
possible to use some physics simulations? Like simulations are very nice. First, like let's train the model on those simulations at various
Mhm.
conditions, and let's now do this physical task in which like the things will now the model will get trained in 10 times only. Like, is it possible?
It's a great question. Yeah. So this is a whole field called simulation to real training. I think it's interesting. Like I've had a few works on this previously as well. The issue we see is that for a lot of real world problems, just modeling them into a simulator actually takes quite a lot of time, right? So let's say I want to figure out how to open a door, right? So let's say I don't know, let's say like at your home you have like a drawer, and I want to figure out how can a robot open that drawer. Now if I'm doing it in simulation, I need to model the whole drawer in your home, right? So that's going to take a lot of time, right? So because I need to model that into the simulator. Instead of that, what we're saying in Win at least is that using the stick in like 20 minutes, I can sort of show you a bunch of demonstrations, and just from that, you automatically know how to, you're, I mean, not after learning, you're able to make a robot open that drawer. So, so yeah, maybe just to
Yeah, it's
summarize that, yeah. So learning in simulation is definitely an interesting idea, but trying to figure out how to make the simulation match the real world, that is not an easy problem. Okay. Any more questions here, or should we move on?
You can move on. Yeah.
Okay. All right. So I've talked about reinforcement learning, and now for the last part of the talk, I'm going to talk about adaptation algorithms. All right. So for adaptation, uh, I think a nice way to motivate this problem is this thing called object sliding, or a task called object sliding. So let's say you have an object on the table over here. This is this like lunch box with some water inside it. Okay. And your goal is given a specified location on the table. As you can see that on this table, there are a few markings over here. Your goal is to figure out how to slide this object such that this object rests, it comes to rest on one of those locations on the table, right? So you may think it's a very easy task, but it is actually quite a hard task to get right. And the way we found out it's quite hard is we actually asked some human subjects to human volunteers to run this, right? And so we specified some locations on the table and asked them to slide the object such that it reaches here. So this is one example which I want to show. So I think the human will first point towards which location he's trying to hit, and then slide the object so that the object rests at that point. Okay, so let's see this video. Okay, so he pointed towards it, and now he's going to try. Oh yeah, and he just completely fails, right? It's just a complete failure of trying to solve this task. So the reason solving this type of task is hard is because you need to know a lot of information about the environment before you can solve this task. You need to know what the mass of this object is, what the friction of the object in the table is, what's the damping of the environment, right? You need to figure out all of this before you can sort of precisely solve this problem. Now, how do you actually get this information? How do you actually understand about the environment? You have to interact with the environment. You have to play around with the object, maybe slide the object a little bit on the table, right? So this is the insight of the following work. Okay, so in terms of a more technical problem, over here, what we're going to also do is to try to be able to slide these objects where where in the training time, we see objects and environments which are not the same as what we see in the testing time. Right? So we have a mismatch between what we're going to see in train time and what we're going to see in the test time. So because of this sort of a setup, we need to now figure out an algorithm that can adapt quickly from the train, from what it's seen in train to what it can do in test time. All right, so let's look at one solution for this object sliding problem. Okay, so a classical way of doing this is called system identification. Right? So the way this works is, I first take this object, I do lots of slides. So this is like a green cup, right? So I'm going to do maybe 4 slides. Each of those slides is numbered 1, 2, 3, 4. Now from this prior information or the past experience, I'm going to figure out what the exact information of the environment is. Right? So I'm going to either learn or have a system identifier, which is going to be explicit. So it's going to give me explicit numbers of what the mass of the object is, what the friction is, what the damping is, and any other environmental information that I would need to solving this task. And once you have this information, you can then train a behavior optimizer, right? So now let's say you have a sliding task, so you can now train a policy to slide the object using this information as well. So this sort of strategy of doing explicit system identification followed by doing a behavior optimization is quite a popular idea. If you're interested in how this is used in the RL context, have a look at the UP OSI work. So I've also put a reference to it over here at the bottom. So this works well if you're able to actually train the environment where you have access to these environment labels. Right? So if you're training a policy or if you're able to train this sort of identifier where you have access to what the mass, friction, and the damping is, it could work well. The problem, of course, is that in the real world, if I show you a cup like this, and if I ask you what is the true training label, like what is the true mass, friction, and damping, this is going to be a really complex process of trying to figure it out. Plus, there may be other environmental effects that you do not even know what they are. For example, it could be air resistance, right? Like, how do you even model that? Maybe for a small object, it doesn't matter, but for a larger object, the air would actually matter. The second issue over here is that um, sort of trying to figure out what the mass, friction, and the damping is assuming that the effects of mass, friction, and the damping are decoupled. It means that given observations, I can actually figure out what the mass and friction are, which is not always true. So in our work, what we're instead trying to do is instead of doing explicit identification, we're going to do something called implicit identification. So instead of outputting, the exact explicit uh, parameters like mass, friction, etc., we're now going to output a representation. So this is going to be an encoding of the environment. So just to contrast this with what we saw earlier, previously we were learning a representation from a high dimensional visual observation. Now we're going to learn a representation of the environment itself. So then once you have this environment feature, also once you have this environment uh, a presentation, we can then use that for a behavior optimization. Okay, so let's see how this is done. So step one is this process called context summarization. So let's say I've seen n examples of interacting with this object in the same environment, right? So I have these like tuples of state action next state, right? And I have n of these sorts of tuples. So this is just like it's just a way to represent the prior experience. Now for each of these experience points, I'm going to feed it into an encoder, which is it's represented as G5. And then I'm going to take the outputs of this encoder and feed it into this thing, which I'm going to call a context summarizer. So what this summarizer is doing is it's taking this n amount of context and it's combining it to give you a single feature representation, ZE. Now we can use any sort of model which can do this sort of summarization. We can either do like average pooling or like max pooling. We can do RNNs. We can use a transformer, etc. The only constraint over here is that this summarizer should be able to work with arbitrary n as input, right? So it should be able to handle a context of any length. Okay, so now once you have this ZE, the next step is to do a dynamics prediction task. So in the same environment, I'm going to look at another example where I start at some state SP, I apply some action AP, and then I end up at a next state S hat P. So if I had a good contextual understanding of this environment, it would mean that I can make a better prediction of what comes next, right? So this is the key important point to train this whole process, right? Like how do we know that we actually got a good feature of the environment? The way we are saying that we got a good feature is if that feature helps you predict what's going to happen next. Okay, so then to train this model, we just create a loss, which is L2 loss at the output of the prediction model. And then we propagate that loss throughout the whole architecture. So through the dynamics model and through the context summarizer, and then through the encoder itself. All right. So let's see how this model works, like how well does this model work. So we first experimented in simulation, and we look at a prediction task. So the goal is to predict what's going to happen next. The interesting thing now is we're going to change the environment, right? So we can have a hopper where each link has a variable mass. We can have a humanoid where again each link has variable mass, there's variable friction, etc. And we run several experiments on this. The interesting thing we note is that if you do explicit identification, for some environments, you get high performance, right? So in explicit identification, you are able to do this because in simulation, you actually know what the mass and friction are, right? So you can actually, it is feasible to train this in simulation. But we're seeing that, even though for some environments it does well, for a lot of other environments, it actually is not able to do that well. And the reason it's not able to do that well is because of the decoupling problem, right? So if you have an environment which is quite complex, just from a few interactions, it's very hard to figure out what exactly the mass was or the friction is, because the effects of mass and friction are often coupled in how the system behaves. In contrast, our algorithm, which is called IDA over here, it does quite well. So we experiment with various versions of it, where we use the average summarizer versus a RNN one versus a transformer one. Right. So all of them do quite well. In some cases, the transformer wins out. In some cases, RNN wins out, and in some cases, the average pooling wins out. But the sort of high level to take away is that in most cases, the IDA models do much better than prior baselines. Okay, so it clearly works well in simulation. Let's see how well it works on the robot. So the robot, our task is there's an object on the table. There are specific goal locations on the table, and the robot needs to figure out how to slide this object to these goals. So when we evaluate this model, we are going to use objects that the robot has not seen before, right? So we can actually evaluate how well this robot is able to generalize to test set objects previously unseen. So here is the sort of video experiments of this. So on the left-hand side, it's our model, which is doing this implicit identification. So it has prior context of interacting with this object. On the right-hand side, it's a domain randomized model, which it doesn't have context of this object. Right. Then on the table, you can see this X mark. The X mark, it signifies what the goal is. For each experiment, the goal will change so that um, we can actually investigate if it can actually reach multiple goals or not. Okay, so I'll play the video and you can start seeing this videos here. So hopefully you should see that on the left hand side, it's able to reach the goal much closer than on the right hand side. All right. So then we also run this across all of our models, across other baselines, and in general, we see that these IDA-based models, they do quite well, much better than our previous baselines. And across all of them, we see that the transformer-based models are also the ones that actually have the highest performance. Okay, so with that, that ends all the things I wanted to speak about today. So I talked about how to do feature or representation learning, how to do RL, and how to do adaptation. So here are the three main problems, and with this, I'll end my talk for today.
There's a question in adaptation. Actually,
Yeah.
you referred to the baselines and how your model is improving.
Mhm.
How exactly do you quantify the how good is the model working? How is my robot working? Like for example, humanoid working. How do you
Yeah.
quantify the measure?
So in this task, we are quantifying it based on future prediction, right? So let's say I say that the humanoid is at a specific step in time. So it's at a specific state in time, right? I'm going to apply some action on this humanoid, right? And then the humanoid is going to go to some next state. So the models have to predict where it's going to go next. So a model which can sort of effectively use context should be able to better predict where it's going to go next. And then we measure the mean squared error between where it went next versus where it thought it would go next.
Okay.
I
Yeah.
hope that clarifies it. On
Yes,
the
that
robot
does.
side, it's slightly different, right? Because on the robot side, what we care about is going to a specific goal. So we're trying to optimize for actions itself. So it's a little bit of a trickier problem over here. So the way we sort of evaluate over here is slightly different. So here we say that there's some radius around the goal. So our radius, I think, is 5 centimeters or something. I think it's 5 centimeters because the error in our perception system is around 2.5 centimeters. So if the object can go within 5 centimeters of the goal, we call that a success. So over here, this is in terms of success rates. The highest possible you could get over here is 100.
Okay. Yeah, that helps. So, yes, sir. I guess that I don't have any other questions. Yeah.
All right. Maybe I can go out of slide mode back here.
Yeah.
All right.
I do
Yeah.
have a personal question, if it's okay.
Mhm. Yeah,
I mean, in general, what people think about reinforcement learning and robots is they have a mind of their own. There's a consciousness and everything. Now, as a researcher, how do you view them? You still think they have consciousness, or it's just a set of matrix multiplications and everything?
yeah. I mean, I don't. So I think any AI, okay, most AI researchers don't think that they have consciousness. There are
Okay.
very few people who think that these robots actually have consciousness, right? Because at the end of the day, it's just large neural network models operating in feed-forward ways, at least.
Yeah.
Right? So there's just some high-dimensional information. There's a neural network which outputs something which is low-dimensional at the end. Right? Not sure if you can call that consciousness.
Yeah, like there's some interesting debate going on Twitter, like from OpenAI and DeepMind about consciousness and the NLP models. So
Yeah,
like,
yeah,
Yeah. So we just wanted to
yeah.
hear
I
your
think
point.
it's yeah. I think it's more of a philosophical question, like what is consciousness? Um, it's yeah. At least to me, I do not know much about the philosophy of consciousness, so it's very hard for me to comment much on that. Yeah.
And do you think reinforcement learning will start robot uprising?
Um, I don't know if it's going to be reinforcement learning, but I think it's going to be like if there was to be a robot uprising, it would be through imitation learning. I would say
Okay. Right.
because it's much easier to imitate humans and do things than to just learn from scratch.
Okay. Does that make sense?
Yeah. Hopefully, it doesn't happen soon.
Thank you, sir. That was a
Yeah.
great talk on reinforcement learning and robotics and everything about agents learning from scratch in general. So thank you everyone for coming. Yeah. Thank
Yeah. Yeah. I think it was great to sort of meet all of you and hear your questions as well.